Okay, so first, like I'll just talk about some general stuff that you'll get to see often, which are like common themes between grids problems. So some things like you have to keep in mind are like uh, you have a lot of you'll be doing a lot of like global ideas, like some over rows and some over all columns and stuff like that. So that comes up often, and then you have like some so something like mod n, or like omega, like where omega is a complex root of unity omega power k type of colorings. Or you might even like have to add some sort of like weight to a cell and sort of maybe sum over all cells and stuff like that. That's some ideas that come over. Another idea is like slightly more advanced, is like suppose you have like a grid with some uh, tokens on some of its cells, tokens on some cells. So then like we can consider those cell that, like then we can sort of build a graph like this. So suppose you have a 3x3 grid and you have some, these cells are sort of marked, then like you can sort of build a graph between the a bipartite graph, and one partition of the bipartite graph is the rows. So suppose this is C1, C2, and C3. This is R1, R2, and R3. You can sort of build a bipartite graph between R1, R2, R3 as vertices and C1, C2, C3 as vertices, and draw an edge between them if their intersection is the cell at their intersection is a marked cell sort of. So here you'll draw edge between R1 and C1, edge between R2 and C3, and edge between R3 and C2. So this is some idea that will like come up often. So this slightly advanced concept, but this is going to be very useful. And the technique, also a couple of problems on it, that is like using lasers. It's like really a fancy name to sort of uh, uh, like put into words more technically. Like it's basically a global argument. I'll like talk about it when we solve some problems on the topic. So um, let's get started. Let's actually get started with a problem. Okay. Uh, okay, is the problem statement visible? Is the problem statement visible to everyone?
Yes.
Okay. So did anyone have time to attempt the problems that I sent? I sent them pretty late, so it makes perfect sense if you didn't have time. Anyone attempt this? Okay, guess it's a no, that's fine as well. So this problem basically tells you that suppose you have a grid and you have some cells marked. I'll just make a 3x3. You have some cells marked, right? And for every cell, you define the pebble set sort of. You consider the tokens as pebbles. You define the pebble set of that cell to be the set of pebbles in the same row and the same column as it. Right. So the problem is to find the least number of pebbles you can have, so that every two cells of the board have a different pebble set. So like first thing, if you have like every cell has a pebble in it, then of course like you'd have everything has a different pebble set, right? So the problem makes sense that way, that we are trying to find the least number of pebbles that we can keep on the grid. So how do you like start approaching the problem? So first thing to keep in mind is, in these kind of problems, it's always beneficial to like first find out the equality case and the construction as well. So does anyone have any ideas for the how the construction might look like? I'll draw n cross n equals 5. Does anyone have any idea about how the say uh, n equals 5 case?
Like one is there at least.
Come again?
Like one is there at least. You don't have any pair then.
I don't get what you're saying.
Like the number of pebbles, if it is one, it also does once, right?
If the number of pebbles is 1, Is that what you're saying?
Yes, yes.
No, then like suppose you have something like consider let's say this cell, then it has a pebble set this which is empty, and then this like these have like empty pebble sets, right? Or actually like look at these cells, maybe this cell and this cell, they have like the
So
same
like you
pebble
need
set.
to have that no pebble set is empty.
Um, not exactly like you can no pebble set is empty. No, you can have like pebble sets that are empty for something like this. For this one, this is this and this is like empty. Like you can have like for the problem where you need no two squares of the same pebble set. Is that a claim? Probably not sure. So like, can you think of a equality case for this first? So like one thing you might start doing first of all is like every cell on the diagonal has like a different like sort of row and column associated with it, right? Suppose like if you first of all place a cell on every a pebble on every cell of a diagonal, then you're safe, like because these guys have different row and columns associated with them. So obviously you can guarantee to put 5 cells without any harm. So can you how many more cells can you put so that no two of them have the same pebble set?
Like no, not no else pebble can be there, because like if it is there, then it will rely on some other pebble set.
Can you repeat what you said?
Like we will have, if we like this is the maximum construction rate. If we have more than this pebble, then in this construction we would have like two pebbles lie on the same pebble set.
No, you still can add more pebbles to this configuration, and you can still like ensure that no two squares have the same pebble set. Yeah, that's what I'm asking you to do. You can still add more pebbles. These pebbles, these guys have completely like disjoint pebble sets altogether, right? Like these guys. So makes sense adding drag to the square. So like one hint is like suppose you add a square here, add a pebble here, and add a pebble here. Does anything like change? Like are there any problems? Does this work or not? Like what I just drew now. I basically filled the one diagonal and then half filled the other diagonal. Yes. Something like that. How to try to minimize this? Yeah, we are trying to minimize number of pebbles. So you suggest like trying some lesser case than 5, like suppose n equals 3. Is that what you're suggesting at all? We can do n equals 3 as well. That's fine. So suppose if you have n equals 3. So suppose you first put something on the diagonal, and then if you put a pebble here, are we still fine or are there problems? Number of pebbles at most 4. Why? Don't understand. No, like if you have way too less pebbles, then you will have a lot of stuff having the same pebble set, right? If you have like say someone suggested put like as 5 pebbles along the diagonal works. Don't get what like wait a second. I think I confused myself. I'll
Like
just
in
take a look
n
at it.
greater than 5, then there will be like some two pebbles that lie on the same row or column. So like they are sharing the same pebble set, which is like a contradiction.
For the diagonal case,
No, no, like for any case, if we have like n is greater than equal, and like the number of pebbles is greater than the size of the side,
okay,
then
suppose for this.
yes, yes. Then like we will have that two pebbles lie on the same row or column. So if they do lie on the same row or column, then we would have like some two pebbles share the same pebble set, which is like in contradiction.
So why is that true? Like suppose you would just have something like, okay, just a second. Uh, yeah, so that is why you need to add like sort of more number of pebbles, right? To have like to ensure everyone has a distinct pebble set. So what you are suggesting is adding very like less number of pebbles, basically. So in this case, what you said, what are you suggesting exactly? This some two guys have the same pebble set. I'm just struggling to find it. Uh, just a second. Yeah, I think yeah. Okay. If you don't have this, let's say you have something like, oops, sorry. Consider, I think 2 points along the other diagonal have the same pebble set. Yeah, so that is what I was trying to say. Just a second. So suppose you have something like, oops. Yeah, so consider this square, right? So it has a pebble set this, right? And consider this square, so it has also the pebble set this, right? So these guys have the same pebble set, and hence it like cannot work. Does that make sense? So the diagonal case is like not valid. You have like these two guys having the same pebble set. So you do need to like add more pebbles sort of to ensure distant pebble set. Does that make sense? Does anyone have any questions regarding this?
But like they already have a distinct pebble set, all the pebbles on the diagonal.
Like they don't like, suppose you suppose consider this square, right?
Wait, can you just mark the pebble set of all the pebbles on diagonals that are on a one diagonal only?
Okay, so suppose you consider this square, right? So its pebble set is just this, like its pebble set looks something like this,
Yes, yes.
just this, right?
And for like
But
the
suppose,
diagonal, it is distinct. Like for diagonal, the
yeah, for diagonal it's distant, we are fine. But like suppose something like you have this here, uh, consider the red dot. By the red dot I just mean to highlight that square and this square, okay? The blue dots are still the pebbles. Then you have something like this guy has a pebble set this and this. So these two guys, these two blue dots, so these two blue dots, and this guy also has only these two blue dots as its pebble set. So they have the same pebble set. So you need to add more pebbles. Does that make sense? So like it turns out like if you play around with the configuration a bit, it turns out that like the maximum sort of is reached. Like you get the optimal construction when like something like this happens. Basically you fill one of the diagonals and then you half fill the other diagonal, something like this. So you can like try to find this for yourself for a while. but like this is supposed to be the optimal configuration. And check that this works. It's easy to check that this works. Convince yourself that this works. So I'm interested in the proof of this bound. So like, can anyone suggest like how we can try to like sort of uh, prove the bound? And this like guarantees something like 2021 plus I think how many? This 2021 plus 1010, right? So this is like whatever 3031, I think, yeah, 3031 cells. So according to our construction, this should be the answer for the least number of cells which have like pebbles on them. So does anyone have any ideas for the proof? Like how do you get to the bound? So like suppose you had a column or a row which is like empty, right? So what can you say about the structure of the other rows and columns depending on it? So suppose you had this row has nothing. The first row has like no cells at all, right? And no pebbles on it at all. So what can you say about the other rows? So suppose I'll just shade one of the rows. Suppose this guy is completely blank, right? So can we have another blank row, like no pebbles on it? So like you can feel free to like unmute yourself and say, because checking the chat is tedious. So what happens if you have another blank row, right? So suppose if you have like another blank row, then you just run into a problem with something like this, because this guy and this guy are now going to have the same pebble set, right? Because it just depends on the two in the yeah, that's what I was saying. So basically these two guys have the same pebble set. So similarly, like can you have like, so similarly try to experiment with the idea, like can you suppose you have another blank sort of blank row, can you have a pebble set with exactly one, sorry, or a row with exactly one pebble on it? Is that possible? So suppose you had just a single pebble here, right? Then look at like the pebble set of these two guys. So all the pebbles that these guys might have lie on this column, right? Because both these rows are otherwise empty except for this. Sorry. So they again have like the same pebble set. So this does not work out. So we would like need so this gives a claim. So if one empty row or column, all other rows have at least two pebbles. Does this claim like, do you understand where the claim comes from? Is it clear to everyone? Feel free to ask if you have any questions. So like I'll move on. So this means that if you have an empty row or column, that will just give you something like 2 times 2020 cells, right? Which is like very could you repeat the case of one pebble? So suppose you have one pebble only here, right? So now look at the pebble set of this cell and the pebble set of this cell, right? They lie in the same column, and the only other pebbles that they can have is like only in this column, right? Because these parts and these parts are not contributing to any other cells. Again, like this part is completely blank, so it's not contributing to another cell. So for these two guys, the only pebbles they can have are along that column, so they'll have the same pebble set. Okay, cool. Okay, so so now like we have dislodged the case where there is like one row and one like empty row or one empty column. So henceforth we just assume that we have all columns have like at least one pebble. So let's say let the number of rows with one pebble be x, right? So the number of total number of cells, no, total number of pebbles, let's call the total number of pebbles something like t. T is at least x plus 2 times n minus x, right? So now can someone like suggest another way of getting a bound? Like how do you get the other bound on uh, x? So suppose once again by what we did, suppose you have like one guy, this is one guy which is like uh, so suppose this is one guy only having one pebble, and this is another row which has only one pebble. I haven't drawn the pebble yet. So can it be possible that this pebble is also has the shares the same column with the first row? So this is, and call these kind of rows like good or something. So good rows have only one pebbles on them. So suppose this is a good row, and this is a good row as well, right? So can it be possible that these two guys share the same column? Why not? So like by what I just discussed, once again you see that yeah, they'll have the same pebble set. Just a second, just move the chat somewhere. So they'll have the same pebble set like we just discussed. So if you look at this column, since nothing is contributing to their pebble sets along the rows, you'll have the same number of pebbles along the column, and that will be their pebble set. So this can't be. So you basically get another observation. These x pebbles lie in x different columns and x different rows. Okay, that's cool. So any other ideas on how to like proceed with the problem? We all need like, I guess we need like one more bound, right? Because we have some information on t, which was trivial, but we need one more bound to be able to solve the problem. So we do know something very nice, that is, if you have x guys, then they have the same pebble sets. Sorry, they lie in different, sorry, I just messed it up. If you have like x good rows having one pebbles in each of them, you have like they are in a sort of a like diagonal fashion in a way, because like they share the different rows and different columns. I'm just like writing it like this. Any more ideas? And the columns are gonna run. So these rows are completely empty and the columns are this way. So suppose you had like, consider one of these columns, right? So suppose this column had like a dot on like another pebble somewhere here, right? So like, and consider this column as well. Uh, okay, not this. So like, look at the columns. So is it possible for like these columns to also be good in a way? Like how many of these columns that go through the uh, that go through the x different good rows have like sort of uh, just one pebble on them? At most one pebble can be good. And why is that? That is a true observation. That is because like, suppose you call a column like powerful sort of if it goes through a good row having a pebble. So like this column is powerful, but this column is not powerful, right? So this column goes to this pebble and this column goes to this pebble, and suppose that these are the only pebbles that are present in those columns, right? So then again, yeah, so this is the same kind of contradiction. So you take the pebble set of this guy, I'll just use a different color, pebble set of this guy and the pebble set of this guy, right? They again have like the same pebble set. So again, this gives you a contradiction. So this basically tells us that any, okay, so I'll just define powerful column. Powerful column means passes through a pebble of good set, pebble of good row. And any powerful, okay, no, not any, like, okay, uh, so this way. At most one powerful column is good. So what is the bound that we get on the number of rows, on the number of pebbles, now that we are looking along the columns? Anyone can say that? So there are t columns, not t, sorry, x. So there are x columns that like go through each like pebble of a good row, right? So you found that you can have at most one of them having only one pebble, and all the rest of them will have two pebbles at least. And there are n minus x columns remaining, and we already covered the case where we have like an empty row or an empty column. So they will have at least one in each of them, right? So this gives you two inequalities. That is this, what we got like last time, and this is what we get this time. E is at most 1 plus 2x minus 2 plus n minus x. So when you sum them up, I think it gives you 2t is at most, does it give you? No. Okay, so x and x goes, yeah. And like, so this gives you basically the bound you want. So does this part make sense? Does everyone understand what is happening towards the like the final bound? So we got one bound. So after we assume that you cannot have an empty row or empty column, you get a bound by simply noticing that you cannot have like two good rows having the. I didn't understand the second one. So now suppose you're trying to scan the pebbles while looking at the columns, right? So like think about the columns and how the pebbles are in them. So first of all, you can have two types of columns, that is powerful columns and non-powerful sort of. So all the non-powerful columns will give you at least one pebble each, right? So this gives you this term. Okay, among the powerful columns, this is the one we discussed. This is the powerful plus good column. And these are the powerful but not good columns. So does this make sense? Now does the bound make sense? So like the powerful but good column, there is at most one of them. So that gives you one. There are x total powerful columns. So that gives you 2 times x minus 1. And the other ones which are not powerful at all, they'll have at least one stone in all of them. So that is n minus x. And you sum them and it cancels out and you're happy. Does that, so does this problem make sense? Like, okay. Does anyone else have any questions regarding the problem? You can like just unmute yourselves and ask. If not, I'll like switch to the next problem. So I might have to take some time after after the allotted time. If I kind of want to cover some problems, we'll see. I might have to take like maybe 5-10 minutes. Okay, just copy the fourth problem. Okay. So does everyone like see the problem statement? So this is one problem where you will see like how useful it is to like view like view tokens as sort of subgraph of km comma n. So we'll come to that. So first of all, does everyone like understand what the problem is trying to say? So you have like a grid, right? 4m cross 4m, and you have some cells in them, and you mark some of the cells blue, right? So just mark them blue. And what you need is you call two cells related if they share column or row, and condition is that uh, every cell every blue cell is related to at least two other blue cells. Oh, yeah, every blue cell, or every cell is related. Every cell is related to at least two blue cells. So does this make sense? So I like not so this is one of the problems where I feel like obviously it's important to like come up with the state like the equality case for the problem, but I don't really think that at least for this problem it is that important sort of to like uh, I mean it's still important for the answer, but the equality case is not going to really help you to gain an intuition about how to solve the problem really, I feel, for this problem at least. So I'll just like mention the equality case because you guys can try to figure it out on your own. Like it's not really very helpful in solving the problem, I think. So the equality case are like just taking sort of diagonal copies of this apparently. Uh, so okay. So basically put these guys in a diagonal and so on. So this is basically how the equality case works. And so like by one, I represent the blue cell. So this will tell you like there are at least 6m, I think. Yeah. So this will tell you that there are at least 6m blue cells. So what I'm really interested in this problem is actually the bound. Like you can like try to find out how the like how the equality case works out. So to prove the bound, we will like, as we discussed earlier, make a bipartite graph with uh, we'll make a bipartite graph with partitions at row as rows and columns. We'll have an edge if something like you will have an edge if uh, the intersection is blue. Okay, so can you tell me some information about this graph? How do you like? Okay, no. How do you like? So suppose you have a let's draw the 4 case first. So these are some random edges that I drew. So first of all, like let's actually deal with the much simpler case where like one row is empty, one blank row case. So what happens if you have like one blank row? So suppose this row was blank, right? So now you know that all of these cells need to be adjacent to some blue cell, right? But the row doesn't provide any more blue cells. So every column will have to have at least two blue cells, right? So if this is blank, then every column needs to have at least 2 blue cells. So this gives you a bound of like 8m, and this is clearly non-optimal. So now suppose you have the like a graph of, yeah. So suppose now you draw the like bipartite y2. What if all the blues are aligned? I meant like at least 2 blue cells, right? So suppose if you have this is suppose your blank row. So this particular cell needs to have two blue guys in the same row or in the same column as it, right? But the row it is in doesn't offer any blue people, so it will have to get the blue cells from the column it is in, right? But this cell is once again okay, cool, like, but this cell once again doesn't have this isn't blue, so the rest of the column must have at least 2 blue guys, and this is true for the rest of the column. So this gives you 8, and so yeah. So now that we draw the bipartite graph, so now we need to like interpret what the condition every cell is adjacent to at least one, every cell is adjacent to at least one sorry, at least 2 blue cells means. So can someone like tell me how do you like translate the condition into the graph theory stuff? Like we drew a graph where every you draw an edge between, you draw edge between the partitions if the intersection is blue. Okay, so suppose this represents the row set, and this represents the columns, and edge means that there's a blue cell in there. So what does the condition every cell has at least 2 blue cells mean? For every C and R, degree R plus degree C is at least 2. Is that enough? Is that enough? So like, suppose, I don't think 2 is enough, because suppose you have this, right? So suppose this was an edge and this was an edge. So think about this cell. So suppose this is the only thing this is true, and you don't have this edge, okay? Suppose this edge doesn't exist. So think about this guy. This guy only has one more cell which shares the same row or same column as it, right? So this basically the problem is telling you that every edge has at least 2 other edges which share one of its ends, right? So can you think of how that translates? So the condition is actually degree R plus degree C is at least 3, I think. Yeah. So can you think of a more easier way to put that, like a more easier way to put that? There is a cycle in the graph because the total number of how do you get there's a cycle in the graph? Hey, I'm not sure how you like prove there's a cycle in the graph. As every edge is sometimes must be connected to 2 other edges. But suppose you have something like this. This is not a cycle, right? Uh, this isn't a cycle, but this is good. This is good enough. Oh, is it good enough? Yeah, I think it is good enough. I mean, well, it. So we can continue. Or no, this doesn't like this. I don't think that is necessarily true. So like, what I was actually going to hint at is the idea of like connected components. So basically what I was saying, like every edge is adjacent, like has at least 2 more edges adjacent to one of its ends, right? So this basically tells you that the connected component, each connected component has at least 3 edges. Does this make sense? Does like this claim make sense? feel free to ask. This is basically the main idea behind the problem. So if you get it, so like that really is a major step in solving the problem. Also, like, I'm not sure why you say there's a cycle in the graph, because like think about what we are trying to prove, right? So we, how many vertices do we have? We have 8m vertices, right? And how many edges are we trying to have? We are trying to have like 6m we are trying to have 6m edges. So like I don't think there should be like I don't think there's anything forcing us to have a cycle in the graph. I don't think that claim is correct. I got a counter example. Is there can be no cycle, exactly. So the idea behind interpreting the condition every cell has at least two related blue cells is you think about it in terms of connected components. Another motivation for that is something like, so you can, you know that like so this is kind of known. uh, so if E is n and edges is k, then there are n minus k connected components. Just a second. Little. Later. Yeah, okay. Sorry about that. Okay, so suppose if you have like n vertices and k edges, then this is kind of known, like the number of connected components is n minus k. So that this might be another like idea sort of to go around to think about connected components. But I think this is quite kind of natural to think about it. So like this condition basically tells you two things, that one of them is like each connected component has three edges. Another one is each connected component has at least four members, right? So is this claim, does this claim make sense as well? Do you understand why this is true? So basically because of the same fact, like if you have something like this, let's say, then like these guys are all in the, oops. So suppose you have something like this, let's say, this is still like working sort of. And again, this connected component has like four. Screen sharing has stopped with this. Let's just stop. Okay, just a second. Ah, uh, yeah, just a second. I think I clicked on exit or something. I'll just de-share my screen. Okay, is my screen visible? Is the screen visible? Hello. Wait a minute. Okay, so I'll continue. Uh, yeah, so like, so now this condition tells, so like we came to the conclusion that every connected component has at least three edges, and every connected a component has at least four vertices, right? So what does this tell us? So there are like 8m vertices in total, right? And so this basically tells you that there are at most 2m connected components, right? But then you know that if connect number of connected components is basically uh, v minus e, as just I said above. So basically this tells you that V minus E is at most 2m. So this gives you E is at least 6m, like we wanted to prove. So does this proof make sense? Are there any questions regarding this? I'll just share one problem that is actually not in the problem set, but it's like a really nice problem. So I'll just share this. Just give me a second. Hmm. Okay, so if anyone has any questions regarding what we have covered till now, like feel free to ask. I'll just give another problem meanwhile.
Could you please go over the construction again?
Oh yeah, sure. Actually, it's probably better if you guys like try to figure out the construction by yourself. I'll just like mention the construction for the 4x4 case, and I guess you can like try to sort of build from this. So for the 4x4 case, the answer is this. So yeah, does that make sense? So like uh, try to like maybe the problem I just can try this for a while. Maybe I'll just be back from the washroom. But this doesn't immediately generalize. Yeah, it doesn't immediately generalize. So like try to find how this like works for an 8x8 case. So try to figure that out. I'll just be back in like a minute. So try this problem for a while. The hint is obviously like try to use some graph stuff. Hello. So am I audible? Am I audible? Okay. So let's try this problem. So some optimizations that we can like place, which like sort of help us to write the solution. It doesn't really affect uh, the way we think about this problem. So first of all, like make sure like you understand what this problem is trying to say. So like you have some real numbers written on every cell of the grid, and it turns out that for every row, like for every row and column, the sum of the real numbers is an integer. To prove that, you can like replace any x with this or this, such that uh, the column sums and the row sums all remain the same. So some optimizations that we can use are like, let's say, just assume that if any entry is an integer, then it's just 0, because we don't really care about non-integer and about integer entries. And if non-integer, then just assume that it's between 0 and 1. This will probably ease our work, right? So well, so again, like we'll try to use I try to approach this problem from a graph theoretic perspective. So suppose you have like an m cross n grid, m rows and columns. So suppose you draw the bipartite graph, uh, like you draw the bipartite graph H with partitions R and C, right? R denotes the set of rows and C denotes the set of columns, and you draw an edge between these guys if they have a non-integer entry at their intersection. Let's say, so suppose this guy have non-integer entries. So any observation that you guys can maybe point out about the graph in general, what we should be looking at? So think about it like you draw an edge if and only if the integer, if the uh, intersection of that row and the column is a non-integer entry, and all the rows have integer sum and all the columns have integer sum. Does that give you any direct claim about or observation about the problem? Maybe try to think about it for a minute or two. So any ideas? So what I was hinting at is like it's rather simple. So suppose you have any vertex x. Okay, so what can you say about its degree? Like, can it have degree 1? If it has degree 1, that means that it has only one non-integer entry in that entire row or that entire column, right? But one non-integer entry cannot, like, but then you need to have the entire row sum to be an integer entry, right? But that cannot be true. So suppose you had like the only one edge corresponding to 0.5, and because we assume that every other integer entry was 0, so you would have that column sum or that row sum is 0.5, which is just, you can't have that. So you can't have a degree v equals to 1. So this basically means that degree v is at least 2 for all the vertices of the cycle, right? So what does this mean? So if you have degree v is at least 2, what does this tell you about the number of edges? The number of edges is at least how many? Like, what if degree v equals to 0? We don't care about it in that case. Okay, so like this is kind of the trivial case. If you have like every degree v equals to 0 basically means like you don't have any integer. Yeah, you just delete the row or the column. You don't have any non-integer entry. Everything is an integer over there, so you just don't really care about it. So degree v is at least 2. So this basically means that if you like do you so then like using 2 times e equals to summation degree v, you basically get e is at least v. So what happens when this condition holds? What does this imply? This is something you might have seen in your introductory graph theory lesson. You have a graph and the number of wedges is at least the number of vertices. Yeah, that is the observation I was looking at. So this basically tells you that if you have, so this is basically a very well-known lemma in graph theory. If e greater than v for any vertex, for any g, then g has a cycle. So we will use this lemma, right? So we now know that our graph H has a cycle, right? But H was also bipartite. So this means this cannot be an odd cycle. So this has to be an even cycle. So now do you have any ideas? So suppose now obviously you're going to work with the even cycle. So suppose if you have an even cycle, suppose this is R1, this is P1, this is R2, this is T2, this is R3, this is T3. Can you do something with the even and odd cycles? So suppose this number is 0.5 here, this is 0.7, this is 0.2, this is 0.5, 0.3, let's say 0.11, 0. Let's not have 0.1. Let's have 0.1 and let's have 0.4. So can you do something with this cycle? Any ideas? So one thing about even cycles that is like often used is like we sort of, one very common idea like used with even cycles is like there has something to do with like taking alternate edges. So this is idea is kind of hard to think about, so I'll just like give it away. So there's also like very useful idea that comes up in graph theory problems a lot. So what we do is basically, suppose you see the 0.1 here, right? So we will basically take the lowest value, the lowest edge width sort of, and deduct it from there, from that edge, and then sort of like keep on deducting it. Like, so what I'm basically mean, like if you have a 0.1 here, so you deduct 0.1 from this edge, add 0.1 to this edge, then deduct 0.1 again from this edge, add it to this edge, and deduct it from this edge, and then again add it to this edge, right? So what results is something like this. So this edge now has a value of 0, which is equivalent to taking the floor of 0.1, right? And these edges have value 0.5, 0.4, 0.8, 0.1, and 0.4, right? So now what does this tell you? So like whenever you do this kind of an operation where you look at the even cycle, you look at the edge that has the least weight, and then you deduct that weight from that edge, and then like just alternate. Like if you're deducting, let's say, epsilon from one edge, you add epsilon to the edge, the next edge in the cycle, and so on, and you alternate between the edges. So you find that if you chose the least number, then the least number gets basically substituted to its floor sort of. So if you have like a 0.5, it becomes a 0.5 as the minimum, then the 0.5 becomes a 0, and so on. So what this does is basically this deletes one edge in the original graph edge, right? And because we are basically taking its floor. But what it also does is like it leaves us with a new graph, let's say h dash, which has one less edge than edge, right? But it still has all the properties that edge had. Like, so I'll just go to the next page. So delete the 0.1 edge, get new graph h dash. So h dash has lesser number of edges than h, but all the same properties. But by all the same properties, I mean that this guy also has an even cycle and we can do the same operation on that even cycle as well. So we can just induct it down on the number of edges. Does this solution make sense? At least the last part of the solution. The graph theory part wasn't really the hard part of the solution. I do think that this part was the real like meat of the solution. Does everyone understand the argument in here? Like where we alternate between the even cycle? If anyone has any questions, feel free to ask. Does anyone have any questions regarding this? Is it clear to everyone? I'll just like still just go over the proof once again. So what we did was first we interpreted this system as a graph sort of, we drew an edge if they had a non-integer entry in them. We understood that you cannot have like a vertex with degree just one, provided there's no isolated vertex. If there's an isolated vertex, we don't care about it. So provided that there's no vertex with degree one, so that implies that the graph is going to end up having a cycle, right? But since it was a bipartite graph, we understand that the cycle has to be even, right? So the main idea of the problem is like you kind of like alternately deduct and add the minimum edge weight in the cycle to all the edges of the cycle. So at the end of the process, you make one of the weights an integer. When we delete zero, I'll just complete what I was saying. So when you like delete, like just add and subtract the edge weight, so the minimum one becomes an integer. You take its floor basically, right? And the other and you get a new graph basically, right? So in the new graph, you will have the similar conditions as the previous graph, but you will have some number of edges less, right? So like at least one edge will be less than the original graph. So and the new graph, which has one edge or more edges less, that will have the same properties as the previous graph, right? In sense that it is still bipartite, it still has a cycle which is an even cycle and can still do the same operation on the even cycle, right? And hence we can sort of induct down on the edge weights. When we delete 0.1, yeah, there you go. We are not adding 0.1 to all of its edges. We are just adding it to I mean, we are not adding 0.1 to all of its edges. Like we are adding it only to the alternate edges. So like, suppose you have, but I still get your question. So you add, suppose you deduct in here, then you deduct here, and you add here, and you add here, and you add here. So again, like to ensure the fact that, so first of all, if you want to ensure the fact that all the columns have the same sum, so just note that or to note that, so like for every column, you are just like adding and subtracting the same thing, right? So if you, for this, suppose this is a row, let's say, so for one cell you are okay, but if on this is a minus epsilon and this is a plus epsilon, if on several iterations the same edge happens to get an increment and eventually it increases beyond its ceiling. So basically you want to say, what if something like this happens, like suppose you have a 0.7 and you like repeatedly added 0.1s to it. Okay. I think we could just in that case like repeat if we see that that is happening, we could just do the other process down. So you could just like suppose if the problem he highlighted comes up, a easy fix to that is like if you see that adding it increases it above its ceiling, then what we just do is like do the other way down. So suppose if x is max edge weight, just add 1 minus x to all edges. I mean like add and subtract to all edges. So in this case, so suppose once again you had suppose 0 0.7, 0 0.3, 0 0.4, 0 0.5. Also, you can't actually like increase it above its ceiling, I think, because like increasing it above its ceiling means adding something like more than 1, which is like not happening at all. You can't have more than its ceiling, right? Because I mean, to get 0 0.7 to more than its ceiling, that is 2, you need to add at least like something like 1.3 at least, right? So that just isn't happening. Because if you get something like the maximum thing you can add to it is something like 9.99 and something, which gives you like 1.7, which has a floor of 1. So we are fine. But yeah, so you can, so what I was saying is like you can still like do stuff like this, like not 0. Suppose you just add 0.65. So you can deduct minus 0.7 from here, not deduct, sorry, add 0.3 to here, deduct 0.3 from here, deduct 0 plus add 0.3 to here, deduct 0.3 from here, add 0.3 to here, and deduct 0.3 from here. So that also works out. What if it does from different cycles on several induction steps? In that case, like I think that this just fixes it. Like if you see that you are having like problems with the seeding basically extending a lot, I mean the number becoming too large, then you can just like sort of take its floor sort of forcefully by just doing this. Instead of taking the smallest edge weight, you take the largest. I think that should work. Yeah. Any more questions? So we perform the epsilon operation. I mean, sort of like, so suppose you can basically what I was trying to say is like, if you have something like you, yeah, I think, yeah, basically what you said. So you can like either take max edge weight and add add 1 minus x and alternate, and or you can take here x is less than 1, and or take min edge weight and deduct x and alternate. These are two things. Yeah, basically what you're saying. Any more questions other than that? If there are none, I'll just go to the next problem. If anyone has any questions, feel free to ask. So this is a really fun problem, sort of. There's like really no way I can like sort of really explain any motivation behind this problem other than giving the solution away. Like this is one kind of coloring that comes up really often. So basically the idea is that you're given a so this induction reduces the case of exactly 2 edges. Yeah, this is not reducing the value of the like. So okay, so suppose you have a vertex here, right? Every vertex has like 2 edges in the event cycle, and since we were alternating, one of these edges gets a plus epsilon, another edge gets a minus epsilon. So the net sum in the row is still the same, right? So we are fine. Does that make sense? It does reduce the number of edges, that is correct. The number of edges, where do we eventually end up? We eventually end up where we have no non-integer entries at all. So like what I'm trying to say, by doing this, we ensure that sum remains constant. Right. So suppose you started with the original graph having 10 vertices, 10 edges, let's say. You did the operation once, it resulted in 9 edges. Then you did the operation and it resulted in 7 edges, and so on and so on. It has to stop somewhere. it will have to reach like 0 edges somewhere. So yeah, that's the idea. It stops when you get a tree, but in a tree you will have a leaf, which is not allowed. We talked about that, right? So this is what I mean when I say that the graph h dash, the new graph is, but that does not, okay, yeah. So like, that is what I was meaning. When I said like the graph h dash has all the properties of h, I really mean to say that it is also bipartite, and it will also have an even cycle necessarily that we can be able to exploit, and so on and so on. Yeah. So if that was all, like I'll go to this problem. Does everyone understand what this problem is about? So you have a 3n cross 3n square, and you tile it with dominoes, and what you want to do is you want to color the dominoes in 3 colors, so that every domino has like at most 2 members of the same color. So suppose this guy is red, then let's draw its neighbors, and the number of dominoes of each color is same. So at most 2 neighbors of the same color. Yeah. So yeah, any ideas on this? We want a 6n by 6n square, right? I think it should be true for, is it not? Oh yeah, sorry, of course, it has to be even, sorry. Yeah, sorry. Uh, yeah, n is easy. So can anyone think of a coloring that works? Spoiler alert, it's very explicit. Like, it's not going to be some beating around the bush, like you have some argument like there exists something, and so on. It's going to be like just an explicit construction. So any ideas about the coloring we should be using? So I'll just like kind of just spoil it for you guys. Like, this is like a coloring that is going to come up like a hell lot of times. So basically the idea is you do something like this. So suppose you have n equals 6. I think this is big enough for 6. Okay, I need. So what you first do is you color every cell in the following way. So color this red, red, uh, red. No, I think not this. Okay. I'll just use RBG. That's probably better. Okay. Um, yeah. Yeah. So color the board in this way, right? And what we will do is like, so now note that every domino has like two colors. So the idea is basically color the domino with the color it doesn't have. So something like if you have this guy, right? So suppose some guy like sort of like covers this square. So you will give it this guy color red. So now look at this guy. So this guy has a red color, right? But the guy above it has a green color. The guy next to it has a green color. The guy next to it has a blue color, and the guy below it has a blue color. So this works out. Does this proof make sense? So this is kind of a funny application of coloring. In general, this sort of like cyclic shift sort of coloring is very useful, and you'll see it in some problems, I think. So does everyone get how this problem, how the solution works? Any questions? If there are no questions, I'll like move on to the next example. So does anyone have any questions regarding this? Okay, I'll just move on. This is the next problem. Yeah. Yeah, is the problem statement visible? Induction works. I don't really know if it does, but like the main reason I really selected the problem was to like just show this sort of, or did you to show this kind of quality, or did you like mean for the new problem, the chessboard infection problem? I don't get by what you mean by yeah. That's a new one. Induction works. How do you plan to induct? Okay, go on. You can unmute yourself and say if you wish to. Okay, and if there are no empty rows and columns, suppose you don't have an empty row or a column, then Acha, okay. I don't think that's going to be enough. So I think like one point that you I think one point that you might be missing is like the problem is not telling you that everything above n works. What the problem is really trying to tell you is that everything below n fails. So if you are trying to induct, you have to keep that in mind, that the solution should use something very specific about n minus 1. Like in the way, the problem is basically trying to tell you that you cannot have like up to n-1 cells covered. You must have n cells, at least n cells. That does not mean that everything above n works. So the optimal case is probably just color everything along the diagonal. That basically tells you that there will be some case for greater than n to work. So any ideas? So like anything like about grid problems in general, like do remember that at the end of the day, every grid problem is like a combinatorics problem, right? So like general combo rules like apply, like look for global and local stuff and some other things that you like generally do on a combo problem. So any ideas? So I'll just like show what happens if uh this happens. So suppose this was one cell. Okay, am I being audible? Am I audible? I just got a notification that my internet connection was unstable. So am I audible? Okay, cool. Okay, so suppose this becomes this. So this problem is kind of like the solution is kind of hard to come up with. So basically the main idea is like okay, so I'll give you a hint. Look for a monovariant, something that changes with the process. So any ideas about what the monovariant might be? So any ideas like what to do for this? When something like this happens. So any ideas? So okay, I'll just tell you guys about the solution then. So the idea is like look at the perimeters. So this was a hard problem. So don't feel sad if you're not able to get any problems. Look at the perimeter regions. And is there any claim from there? So any claim about the perimeters of the blue regions? Stays same or decreases? Yeah, that is true. That was actually what I was hinting towards. So the basic idea is that the perimeters of the lake region of the blue regions are, I just said lake because blue, of the blue regions are like non-increasing. Why is that true? So like suppose you had, sorry, this, and you went to this, right? What is the perimeter in this case? So you let go of these two edges. These two edges don't count anymore, but you have added these two edges, right? These two edges got added. So this stays the same in this case. For this case, you see that you have let go of these four edges, right? And you don't have any compensation at all. So this has like -4. So similarly, you can draw something like this. And you can like basically take cases about what is happening. So, right. And again, you notice that you are letting go of at least two edges and you don't have compensation. I'll just mark them with a different color. So it's kind of easy to see by taking cases and stuff that this is non-increasing, right? So basically at the end, you need perimeter to be 4n. But if at most n-1 cells initially, initial perimeter is at most 4n-1, 4n-4. So that's the content. So does everyone understand the solution of this problem? So for this problem, like it was basically telling us like to prove a property that was like to prove that something failed for always, that something always failed for less than n-1 cells. So we try to look at something that does not change throughout the entire process. I mean, is a monovariant through the entire process, and we try to approach the problem that way. So this was quite a difficult problem. So if anyone has any questions about this problem, please feel free to ask. I'll pull up the last problem, I think, for today. Next. Do we have time for another one? Yeah, this problem will be about this. The next one I will. Yeah, so this is the next problem. So try to understand the problem and maybe take a look at it for a minute or two. I'll then tell you about the solution. What do they mean by cell? Which problem? Cell means like a square, like new one. Oh, cut each cell like some just you're given a rectangular piece of paper, so something like this. So this is, I suppose, a 2x2 paper, and this is a cell. I mean, like just the regular rectangular thingy. Suppose you have like m cross n. Okay, probably. Okay, yeah. Okay, so I'll just mention, or just like suppose m cross n board. I kind of wrote the question in a hurry, so sorry about that. So suppose you have an m cross n board where m and n integers. Every cell is cut along one of its diagonals. Prove that you end up with at least 2 n pieces. So I'll just I'll just do the case n cross n for like just take a 4x4 case. That's better for visibility, let's say. So when do we end up with one piece? What does one piece mean? Like one piece basically refers to a connected component, sort of, right? In the in the final graph. So okay, so yeah, I just drew a random cut, sort of. So the idea here is basically, so suppose if you look at all the connected regions that are formed, right? So for example, this is a connected region, and then this is a connected region, and then I think this is a connected region, right? And then this big diagonal square is a connected region. This 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 and this. So sorry about all the mess I caused. I'll just delete it quickly. But do you guys like understand what a connected region means, right? So that the problem is clear. So how do we approach this problem? So first of all, so we'll like try to see how lasers is useful in this. So what we will do is like, so there are two types of connected components in here. So if we look at it carefully, so one type of connected component, you just have like they are like adjacent to some edge of the grid. For example, this one is adjacent to an edge of has like the connected component sort of like formed with one of the edges of the grid, right? But something like this big guy doesn't have any edge of the grid. So these are two types of connected components. So call the ones which have some edge adjacent to the grid as type as just good components, let's say. Right. So we will actually prove. Okay, so like let us try to find out how many good components we have in here. So yeah. So this is one good component for sure. This is one good component, I think. Okay. I'm missing one. Are those all? Oh yes, of course. This one. So how many good components are there? 8, right? So like the idea is like if you treat every diagonal of the square that you have drawn, every diagonal you have drawn as a mirror, sort of, right? And you sort of like so if you like shine a laser through every edge of the rectangular grid, the idea is like whenever the light ray like sort of travels through a connected component and goes back, it goes back through some edge, and this like these edges are like distant. So like this pair of edges are like distant. So for example, what I'm trying to say is like I'll just I'll just like erase this guy. It's just tough. Okay, I'll just use another marker. So suppose you have an ray of light coming through here, then it is going to reflect like this and go back. So these two edges like form a sort of a pair. So similarly, suppose if you reflect and if you like give an ray through here, then it is going to come out of here, right? And similarly, like if you shine a ray through here, it is going to come out of here. And if you shine a ray through here, it is going to come out of here, and so on. If here, then here. Do you get what I'm saying? So the idea is basically like this, because of this, because of how diagonals are, how the geometry of diagonals sort of works, and how like reflection works, you know that whenever you shine a light through one of the edges, it will come out through one of the components through another edge. And this pair of edges is unique. So you can't have like one guy pairing with one edge pairing with two edges, right? So this basically tells you that you can pair of edges so that light ray entering through, so that laser through one edge passes through other, or let's say exits through the other. Right? And every such pair corresponds to one good connected component. Right? Good was like has an edge adjacent to it. So this means that there are at least p pairs. So p good connected components, because you can have p such pairs of edges, and hence at least p total pieces. Because we haven't yet taken into account the inner structure, like how many cuts are there inside the thingy. In the how many connected components are there inside the, like doesn't have any edges. So yeah, that is about it. So does everyone understand how the proof works for this problem? So an extension of the problem would be to like try to solve this problem. Maybe extension, what is max number of CC? Does everyone understand how this problem works? Any questions regarding this? I think I'll end. We could shine the laser at the midpoints for simplicity. Yeah. So yeah, I was probably at the midpoints of the diagonals. I mean, if you just throw it through the midpoints of the edges, let's say, then yeah, I mean, it's the same thing. It is the same thing. So yeah, so that's probably putting it into better language. Like if you like just have something like this, you make sure that it goes through here and then goes through here and then goes through here. How you just write it like this? Like if you, how would you describe this formally? You just write it like I said, like you call the component. So like you just say something like, I mean, I will leave a link to the solution. I'll leave a link to the solution, but you can write it like this, like if you shine a laser through one of the edges, it must like come out, it must exit like to another edge, because after it traverses through a good connected component, and like this you can have like p pairs of edges. So yeah, so p pairs of edges, which means that every such like no matter how you cut the diagonals, you will always have you will always have like p good connected components, and this is basically p good connected components, and hence there would be at least p total connected components. I'll leave a link to the solution. I'll actually just do it right now. So any other questions from the lecture in general, like uh, anything you want to ask, any doubts in general? Otherwise, I'd be happy to end it. So any questions? Okay, in that case, I'll like stop sharing. Just like